Okay, so I'd like to welcome you all to the last installment of quantum computation and isolation for now. So in I will first of all, I'd like to thank everybody for participating in throughout this last half a year or so. We began in early February, and we've had a lot of very nice speakers. And in the future, um, I'm planning to organize some other seminars. I was probably starting the fall semester, and I'll make sure I keep everybody on the mailing list up to date, and I'll announce it on Twitter as well. Anything that I do, and it's more publicly open. So today I'm very happy to be introducing Professor Mark Wilde. So Professor Wilde got his bachelor's degree in computer engineering from Texas A&M University in 2002, his master's in electrical engineering from Tulane University in 2004, and his PhD in electrical engineering from the University of Southern California in 2008. In 2008, he was a visitor at NEC Laboratories America in Princeton, New Jersey, and in the Center for Quantum Technology at the National University of Singapore. From 2009 to 2013, he was a postdoc fellow at McGill University. And in 2013, he was a visiting professor at the Autonomous University of Barcelona and MIT. From 2013 to 2018, he was assistant professor at Louisiana State University. And from 2018 to present, he's been associate professor at LSU. He's a recipient of many awards, including but not limited to the Centre de Recherche Mathématiques Thematic Postdoctoral Fellowship from 2011 to 2013. He was elected as senior member of the IEEE in 2013. He was awarded the APS IUSSTF Professorship Award in Physics in 2014, the LSU College of Science Non-Tenured Faculty Research Award in 2016, the AHP Brookhauser Prize in 2018, and the LSU Rainmaker Mid-Career Scholar Award in Science, Technology, and Engineering and Mathematics in 2019. And today he'll be talking about applying quantum information-theoretic techniques to quantum complexity theory. So please help me in welcoming, either by muting yourselves and clapping or by clapping virtually, Professor Mark Wilde.
All right. Thanks a lot for the introduction. Brings back a lot of memories. I'm going to be telling you today about things that I was doing at McGill when I was a postdoc about almost a decade ago. Oh yeah, and I'm reminded you mentioned one of the awards is called the LSU Non-Tenured Faculty Award, and I just I always thought that name was very funny, that they, remind you when they're giving you this award that you don't have tenure. Anyway, all right. So indeed, I'm going to be telling you, it's kind of like my perspective on problems that I've contributed to in quantum complexity theory, coming to the field as a quantum information theorist. So, if you study quantum information theory, there are certain things that you learn and you know well, and then you start discovering that these concepts can be applied in different fields. And so that was very exciting for me to make these contributions to quantum complexity theory and to continue to do so. And then more recently, we're taking these ideas and implementing them on quantum computers. There's some unpublished work that I'll discuss as well. We'll be putting that in the archive in a week or so. Okay, so there's some things that I wrote in the abstract that was sent out, and I just want to reiterate those points. The main goal, when it boils down to it, the main goal of quantum information theory is to figure out what are the ultimate physical limits of communication. So in order to figure out these limits, we need to have the best physical laws available, and those laws are quantum mechanics. It's our best understanding of the universe at the moment. I will be focusing on, non-relativistic quantum information and computation. And then another goal is you want to figure out what are the ultimate limits of computation. And this is what quantum complexity theory addresses. So I don't know if y'all are familiar with that. And, you should feel free throughout this talk to stop me and ask questions. I think this should be an opportunity for learning. I've prepared 16 pages of material. It's very likely we will not be able to get through it in the time allotted. I will make the pages available to Joshua after the seminar. Okay, so these are two grand goals, and the reality is that they are intertwined, because in practice, a communication device is going to perform computation, and the same is true for a computational device. It's going to perform communication. And so these fields and these goals are strongly linked to each other. And today I'll be talking about a model of computation that has existed for some time. It's this quantum interactive proof model of computation that's used to understand complexity theory. But what I'll also mention is that we can twist things around a bit and try to use this model on near-term quantum computers to understand what their capabilities are. And people are already doing this. Some of them who are doing it might not even realize that they're doing it. And so I'll point out that as well. Okay, so in quantum information theory, what is a simplifying assumption that we make? The focus of quantum information theory is communication. And so the resources that you count are those that are crossing the physical boundary between a laboratory of Alice and a laboratory of Bob. Typically, Alice is the sender and Bob is the receiver. And in order to make progress on communication questions, what you do is you make the simplifying assumption that computation is free. Okay, and that makes the theory a lot easier to deal with, and then we can figure out what are these limits to communication. Okay, and similarly in quantum complexity theory, in the models that we'll consider today, there are other models of complexity theory, in particular communication complexity, where you do count communication. But what I'll talk about today, we'll just be assuming that the communication is free. We will be counting the number of messages that are exchanged between parties. So in that sense, it's not necessarily free, but what we'll allow for is the size of the message to be communicated to be arbitrary. Okay. So, you kind of have these complementary things going on. And if I were to pick an alternative title for this talk, it's something I mentioned at the beginning, it would be how quantum information theorists can contribute to quantum complexity theory. Okay, so that's what I think is interesting, and where I think more work can be done than is currently out there. There's all kinds of problems that are of interest to quantum information theorists, like calculating entropies, calculating various measures of information and distinguishability. And we can try to understand the difficulty of these tasks in the language of quantum complexity theory. And by doing so, we can figure out methods for computing these quantities. Okay, so I want to start, I'm going to start with the assumption that you're not familiar with some of these basic complexity classes, or even if you are, I'll be reviewing them. Okay, so we're going to start out with the basic quantum complexity class of interest, BQP, which stands for bounded error quantum polynomial time. I'm not going to be giving detailed, rigorous definitions of these complexity classes. I'm just trying to give you the intuition behind them. Okay, so BQP, I want you to think of it as the class of computational problems that can be decided with a structure of this form, with a quantum computation of this form. And this is a form of quantum computation that perhaps you're used to if you've studied quantum computing before. So the circuit, it has this simple form. Some number of qubits are initialized to the all zero state. When I write zero, that's implicit for like 0 tensor n, where n is the number of qubits. Okay, so you do this preparation. And I will be making the assumption throughout the talk that these quantum computers work well, they work well and we don't need error correction. So that's going to be a simplifying assumption I'll make for today as well. And in fact, that's an assumption that's made in quantum information theory, like that the computations in Alice's lab and Bob's lab are reliable and free. Okay, so the computation begins by initializing a number of qubits to the all zero state. You then apply a unitary circuit. So this is composed of basic quantum logic gates. You learn about universal gate sets like C0, Hadamard, and the T gate. That's one example. So you execute the sequence of instructions. And that we can do now on the IBM Quantum Experience or other services. And then there's a single output, there's a single qubit, which we call the decision qubit, okay? And the other ones don't matter for making a decision. And you're just trying to arrive at a yes, no answer. And an example would be like, is a given number specified you translate some integer to maybe like a binary sequence, you could ask, is the number prime or not, right? So that's a decision question, and it has a yes answer and a no answer. And what you do is you measure this decision qubit to figure out, whether the computation is saying yes or no. Okay. So, and then there's some terminology that we use. If the measurement outcome is 1, then we say that we've accepted. And if the measurement outcome is 0, then we've rejected. Okay, so going back to the prime example, if we accept, we're saying, indeed, the number is prime. And if we're rejecting, we're saying, indeed, the number is not prime. Okay. So with this complexity class BQP, and with most complexity classes, there's a notion of completeness and soundness. Completeness is that you're accepting when you should accept, and soundness is that you're rejecting when you should reject, okay? And since quantum computation is probabilistic, we give these thresholds, and this number 2/3 is bit arbitrary, but it's a common choice. So we say, the completeness condition is that you're accepting with probability greater than 2/3 when you should accept. So if the number is prime, then your computation that you execute should accept and say, yes, it's prime with probability greater than 2/3. And, if it's not prime, then you should reject with probability greater than 2/3. And so that's the basics of BQP. And here I'm just reviewing this prime number example. Okay. And, the class of problems that can be decided in that can be decided in BQP are those that we consider realistic quantum computations. Okay. That can be done in polynomial time. Okay, and to be a bit more specific, for example, with the prime number testing, you specify you take the integer, you convert it to a binary sequence, and then the number of gates in the circuit should be no larger than a polynomial in the length of the sequence that specifies the number, right? And if that's the case, then we say that the computation is efficient and it's in BQP. Another thing I should say about these probabilistic conditions is that you can repeat the algorithm many times. And if these threshold conditions indeed holds, then through this repetition, you can make the probability of accepting arbitrarily close to 1 when you should accept, and the probability of rejecting arbitrarily close to 1 when you should reject. And so that's like a form, through repetition, it's like a form of error correction. And you can make the computation essentially deterministic for all practical purposes. Okay. So I want to move on, and I'm going to be talking about 3 more complexity classes, and they fall into what we call quantum interactive proofs. And they're parameterized by the number of messages exchanged between what's called the verifier and the prover. So for BQP, I didn't even talk about a notion of a prover. There's only this person who's the verifier, who's like doing this computation to figure out the answer. So BQP can alternatively be called QIP 0 when there's 0 messages exchanged. Okay, so what I want to next get to is a class called QMA. The name's a bit historical. It's for Quantum Merlin Arthur, and there's historical reason for that. But you could also call this QIP1. And the intuition is that there are some problems that are too hard to solve in BQP. And so what we can do is to ask for help from someone who has unbounded computational power, unbounded quantum computational power, okay? So that's an assumption we make for this class, this complexity class. And that person is, we call them a prover, because the idea is that they're helping you to prove the truth of some statements, okay? And so indeed, there are some problems that are too hard. And later on, I'll talk about this famous problem called local Hamiltonian, where you're trying to decide whether the ground state energy of a Hamiltonian is below some amount or above some amount. In that case, if you had the ground state of the Hamiltonian, then that would be helpful in deciding the answer to the problem, But that ground state might be hard to prepare on a quantum computer. And so that's where this conceptual notion of asking for help from a prover is useful in understanding complexity of the task. Okay, so QMA is the class of problems that can be decided by this computational model. It's very similar to BQP, except some of the inputs to the unitary we allow to be inputs that are fed in, we feed in a state supplied by the prover to those slots of the unitary, okay? And then, everything else is the same. Some sequence of gates are executed, and then there's a single decision qubit that helps you decide yes or no is the answer to the question, right? And so the example I mentioned was this local Hamiltonian problem. Yes, the ground state energy is below some amount, or no, it is above some amount. Okay, so that's the complexity class. And the intuition is, I think I said it, but some quantum states are very difficult to prepare, okay? And so you ask someone else to do it. And the assumption of this model, I'm just restating it. The prover is assumed to be all-powerful and can perform arbitrary quantum computations. And this here says, like the assumption in quantum information theory, in quantum information theory, when we're analyzing channel capacities or distillable entanglement, we make no restriction on the quantum computations that can be performed, just to simplify the theory. Okay, so with QMA, we also have completeness and soundness. And the completeness condition is that when you should accept, for example, when the ground state energy is below a certain amount, when it is indeed below a certain amount, there exists a state that the prover can supply such that the acceptance probability, the probability of measuring 1 on this qubit, is greater than 2/3. Okay. And then soundness is that when you should not accept, the acceptance probability is less than or equal to 1/3 for all states of the prover. Okay. So this is an important principle of these quantum complexity classes and the role of the prover. The prover is someone you cannot trust. The prover is always trying to convince you to accept, no matter what. And so as a verifier, you need to figure out some test to decide whether indeed the state supplied is a legitimate state that ultimately should be convincing that you accept. And furthermore, in the case that when you should not accept, there should not be. This is why the verification is important, why we call the person the verifier. There's a test that you're using to decide whether you should accept or not. In the case that you should not accept, there should not be any state of the prover that should convince you to accept. So that's the soundness, right? So, the example of local Hamiltonian, if the ground state energy is indeed above some amount, then there should not be any state that the prover can generate to convince you that the ground state energy is below that amount, right? And so that's the model. So I guess I've already discussed this example of local Hamiltonian, but that's like a nice problem that's in QMA, and you can prove that it's also hard for QMA. I'm not going to talk about hardness results today because I want to focus on the algorithms that I'm going to get into. Okay, but this problem of local Hamiltonian, because it's complete for the class, it kind of characterizes the class. So you can think of QMA in terms of this local Hamiltonian problem. Okay, so now I want to mention an idea that people had quite some time ago. This is now like a famous paper. I looked it up today. It's cited like 1,200 times. And their idea was simple. They said, okay, let's replace the quantum prover with what's called a variational circuit, and then use a hybrid quantum classical approach to address these questions like the Hamiltonian problem, figuring out the ground state energy. Okay, so their idea was, rather than relying on some fictitious prover to generate the state, come up with a circuit that can attempt to generate this state. Okay. And the circuit can have a structure where like maybe there's a layer of controlled knots between qubits, between adjacent qubits. And then there's another layer of single qubit unitaries that are, these unitaries are parameterized by certain angles. And then you can repeat this structure a certain number of times. And so with this variational circuit, you tune these parameters and you attempt to make the state that maximizes the acceptance probability, right? So that can be done for the local Hamiltonian problem, and it can be done for many other problems. And this is something that can be done on near-term quantum computers. And there are various studies out there about how robust to noise it is. I myself have not yet worked on the topic, but from a personal perspective, what's still funny for me is that for some strange reason, I was actually asked to referee this paper in 2014. I was looking back at my referee report today, And, in the report, I mentioned to them the importance of the connection to QMA and how this is, what they were doing was some kind of approximation of QMA. Like they're trying to find this state that maximizes the acceptance probability. So the way the variational algorithm works is that the acceptance probability is something you can think of as a reward function. So you're trying to maximize that function. And that's the part it's easier to use the quantum computer to estimate the reward function. The Hilbert space is so large that it's not going to be easy to do it on a classical computer for circuits of large size. So instead, you try to do it on a quantum computer. So you do one iteration, you do one iteration, which will involve several repetitions, and you estimate the acceptance probability when there are certain values of the parameters chosen. Okay, and then on the next iteration, you change the parameters, maybe according to some adaptive algorithm or some kind of machine learning algorithm to try to increase the acceptance probability. And then after some number of iterations, you kind of hope that you've found some approximation of the ideal state that the prover would supply. In the case of the Hamiltonian problem, the ideal ground state is what you're trying to approximate. Okay, so that's going to be a common theme throughout this talk, and something I'll mention is that we're going to take the prover and replace the prover with a variational circuit. Okay, and then that's something you can do on current quantum computers, and that's the work that we're doing right now. That's unpublished. We'll release it in a week. Okay, the next complexity class I want to mention is QIP2, where there are two messages exchanged between the verifier and the prover. And it's a generalization of QMA. And the circuit diagram looks like this. So it's the class of problems that are decidable using this model. So first, the verifier is allowed to do a state preparation according to some unitary, send some number of qubits to the prover, who then acts with a unitary on some ancillary qubits as well that can be allowed, send some number of qubits back to the verifier, who does another computation according to a circuit, which in many cases is going to be a test. It's going to be some kind of test. Later on, we're going to see a test for entanglement. We're going to see a test for symmetry. And then the verifier will measure the decision qubit and accept if the outcome is 1 and reject if the outcome is 0. Okay. And then it's conceptually similar to QMA, except now we have two messages exchanged between the prover and verifier rather than just one message exchanged from the prover to the verifier. Okay. And then there's similar conditions for completeness and soundness. Completeness is that there exists a strategy of the prover. The strategy is a unitary that will convince the verifier to accept when the verifier should accept. And soundness is that no strategy of the prover will convince the verifier to accept when the verifier should not accept. So that's QIP2. And then we can go on. QIP3, 3 messages exchanged, 1, 2, 3. With QIP3, to count the number of messages, you start from the final one and go backwards. And so then we figure out that, if there's 3 messages exchanged, the prover goes first. Okay. So it's similar as before, but now 3 messages are exchanged. So what is the idea of these models? That more interaction gives you more computational power. Okay. In QIP1, you can do everything you can do in BQP by, you just ignore what the prover sends and do the circuit, and then you realize BQP. So BQP is contained in QMA. For a similar reason, QMA is contained in QIP2, and QIP2 is contained in QIP3. So those are the containments, and QIP3 is the most powerful. There's a famous result of Kataev and Watrous from the year 2000 that it suffices to have 3 messages exchanged between the verifier and the prover. If you have more, then there's a way to, there's a procedure you can run to reduce the number of messages exchanged to 3 without any loss in the relevant parameters for the interactive proof system. Okay, so that's quantum complexity theory in a nutshell. And what you see is that the communication is, this is like a communication protocol, right? Between like a server and a client, right? And the computational power depends on the number of messages exchanged, and not necessarily their size. But we do assume that the quantum messages are no larger than polynomial in the size of the problem. Okay, so the verifier can actually process what's coming in because the verifier is bounded to do polynomial time quantum computations. All right, so that was a lot of general talk. And the remainder of the talk, which I guess is about 20 minutes, I want to tell you about some problems of interest. And I'm going to start with a simple one that goes back to John Watrous in the year 2002. And it's a way to see like a very famous kind of problem, fidelity of states, in terms of an interactive proof, okay? So here's the computational problem. We suppose that you're given circuits to produce purifications. So there's a circuit U0, U1. I'm using the same symbol to denote the circuit and the unitary, but I think everyone does that in quantum computing. So U0 will make a pure state psi 0 on systems R and S. Same for U1, it'll make psi 1. And these states are purifications of states of interest. You know, when you trace out system R of psi 0, you get rho 0s. When you trace out system R of psi 1, you get rho 1. So the computational problem is given descriptions of these circuits. So the circuits are specified as like a list of instructions, right? A list of quantum logic gates that you concatenate together. You want to decide whether the fidelity of these states is greater than a threshold or below a threshold, where this alpha is strictly greater than beta. We just think of them as constants for simplicity. And the constants will be between 0 and 1, okay? So to clarify a bit, what do I mean by circuits that produce purifications? I mean, when U0 acts on the all 0 state, it produces psi 0, and same for U1 producing psi 1. The other thing I want to remind you of is the fidelity is defined like this. I'm going to put the square to make it have a physical interpretation as a probability. Okay, so this is a problem of interest in quantum computing, quantum information. You know, it's basically asking, do 2 different methods of state preparation lead to the same state approximately, okay? And this can be useful in applications like quantum compiling, like you have some circuit, you have one circuit, and then maybe you want to figure out another circuit that produces the same state, but has a much shorter depth, okay? So this is the computational decision problem. How do we solve it? The basic idea is to recall this fundamental theorem called Ullmann's theorem from 1976, which is used all the time in quantum information, okay? So Ullmann's theorem says that this formula for fidelity is equal to this, this optimization task. So you take the purification psi 0 of rho 0, you take the purification psi 1 of rho 1, and then you compute this overlap and you maximize over all unitaries in the reference system, okay? So this is an overlap formula, and the point I want to mention is that this formula leads to a quantum interactive proof. You know, you can compute the fidelity with a quantum interactive proof. You can estimate it. How do you do so? You take the all zero state, you act on it with U1, and now I'm doing this part of the formula, right, of Ullmann's formula. You send the reference system to the prover. That's the hard part. This formula involves a maximization over all unitaries on the reference system. So that you give to the prover. It's the hard part, and it's not necessarily going to be efficiently computable on a polynomial time quantum computer, right? So you give the hard part to the prover, who sends back the reference system, and then we're going to do this part of the formula. We want to measure, and ask, is this state equal to this one or not? And the probability that you get the outcome it's equal to this state is exactly equal to this overlap formula, which is the Born rule, right? So, I have a typo. I'm sorry about that. I meant to have a dagger right here. Okay, so there should be U0 dagger. So you do U0 dagger, and then you do a measurement in the computational basis, and you accept if and only if all the measurement outcomes are zeros. Okay, why should you do that? Well, if you go backwards in time, if you prepare the all zero state here, and then rather than doing U0 dagger, you do U0, the state that would be prepared is size 0, right? And so this interactive proof system is computing this formula. Okay. I stated previously for QMA that the strategy of the prover is to maximize the acceptance probability. So the acceptance probability is given by this, and then this is the unitary that the prover is doing. So then if we maximize the acceptance probability over all unitaries, we get the fidelity. Okay. So the conclusion of all this is that this is an interactive proof system, and by a direct application of Ullmann's theorem, its acceptance probability is the fidelity between row 0 and row 1. Okay. The fidelity is a number that is generally strictly between 0 and 1. And so if you want to decide the answer to this question, is the fidelity greater than some threshold or less than some threshold, you're going to need to repeat the algorithm. You're going to have to repeat this algorithm many times. But when you do so, there's going to be a problem. The prover does not have to employ a parallel strategy. Like if I'm doing a repetition of this algorithm, a strategy of the prover is to do the maximizing unitary UR every time. But the prover does not have to do that. The prover can act jointly on all these reference systems with some unitary. And so, there's a technical difficulty encountered, which was solved in the paper of John Watrous. There's a clever strategy that you can use for parallel repetition, such that the prover can't trick you into like calculating a different formula for the fidelity. And I'll note, for those who studied quantum information theory, this is very similar to additivity issues that crop up in quantum information theory. Often we're considering parallel uses of a channel, and maybe we're like maximizing an information quantity with respect to inputs, and those inputs can be entangled or parallel, and so it's very similar conceptually to what goes on with additivity. Okay, previously we talked about the variational algorithm for calculating the ground state energy of a Hamiltonian. We can do the same thing here, right? Every time you have the prover in a quantum interactive proof system, you can replace the prover with a variational circuit and do this kind of optimization with repetition. And if you're doing that, now you're the prover, and so you can just act with a parallel strategy and not worry about that. That issue of parallel repetition, it's something that comes up in quantum complexity theory. But if we're now the ones controlling the circuit, then it doesn't come up. So you can replace this prover by a variational circuit you won't be able to realize an arbitrary quantum computation, but for certain states of interest, you could potentially calculate the fidelity. So this was proposed in a recent paper, and these authors, it's a colleague of mine, Xin Wang, and his co-authors. They did this, and they used I don't know which quantum computer they used, but they used one of them as a heuristic method to estimate the fidelity. Although I don't believe they remarked about this, that replacing the prover with a variational circuit, but that's effectively what's going on. Okay, I want to continue. We have about 10 minutes, so maybe I have to pick up the speed. Another problem of interest is to decide if a pure state generated by a circuit is entangled or not. Okay. So here I want to focus, I want to assume, to begin with, let's just assume that the state is product for the sake of argument. So the idea for testing whether the state's entangled or not is that we'll use symmetry of product states. So what do I mean by this? If the state's product in this form where phi and I think this one is called var phi in LaTeX and this one's phi. So these are pure states. Then if we generate two copies of psi AB, the state will be this. And then what you see is that the global state is invariant under a swap of A1 and A2, and it's invariant under a swap of B1 and B2. Okay, so you can then use this circuit to decide if the states product are entangled. Okay, so this is doing exactly what I mentioned here. We're going to use the circuit to make two copies of the state. And suppose that the state is product, then we have, what was it? Var phi here and phi here, var phi here and phi here. So var phi goes here, and then phi goes here and here. The swap test is a famous test that's being used in all the near-term quantum algorithms. So what you do is you accept, you say that the state is product if and only if both swap tests pass, right? Because we said that if the state's product, then you see clearly that A1 and A2 are invariant under swap, and same for B1 and B2. And so that's what the circuit is testing. If you do the swap test on tensor product of mixed states, the success probability will be given by this. That's something you can prove. It's a nice exercise. And so, given the fact that for a pure bipartite state, now let's assume that the state is general, right? So if the state's general, not necessarily product, then one thing that's well known is that if you trace over B1, there's a density operator here. That density operator has the same eigenvalues as this density operator, okay? So you can use this fact, the probability of success for a swap test, and what I just stated to conclude the acceptance probability of this quantum algorithm is equal to this expression, right? Because it's like, this is the probability for a single swap test to pass, like this one. And, these are like independent swap tests. And so the overall success probability is the square. Okay. And this rho A is the reduced state of psi B. Okay. So the way this works is that if the state is approximately product, then the probability to pass the swap test is going to be near to 1. And if it's not approximately product, the acceptance probability will be far from 1. More particularly, this method, going beyond the simple decision, of deciding whether the state is product or entangled, it actually computes an entanglement measure, right? If you repeat this algorithm many times, and then you can estimate this acceptance probability. And what you see here is this trace rho squared. That quantity is related to an entanglement measure for pure states called the Renyi entropy of order 2. So you can estimate that, okay? And then there are other things you can do. And, Steph Folds on the call, she has a recent paper where she was doing all this kind of stuff. And in a forthcoming paper, we're going to have other kinds of tests, symmetry tests that can be conducted to estimate different entanglement measures. Okay. So now I want to move on to talk about entanglement of mixed states. All right. And this is work that I did with Patrick Hayden and Kevin Milner approaching a decade ago. Okay. So the problem is this: given a circuit to generate a state, rho AB, decide if that state is separable or entangled. Okay. So the way that we always do this is that we suppose that a circuit generating a mixed state is a unitary, and you generate the mixed state by tracing out a reference, right? So this is the procedure to prepare rho AB. You act on the all zero state with some unitary. It produces three systems. Reference has some number of qubits. Alice has some number of qubits. Same for Bob. And you trace out the reference, you get the rho AB. Okay. So now how are we going to decide if this state is separable or entangled? We can't use the swap test. It's not good enough. So we need something else. But we will use symmetry. Okay. And we're going to use a concept that's very closely linked to separability, and it's called K extendability. So I have to take a minute to review this concept, but I'm going to do it quickly. So a state is said to be K extendable if there exists an extension state where these B1 through BK systems are isomorphic to the B system, such that, so by extension, I mean when you trace over B2 through BK of omega, you get back sigma. So it should be an extension. And furthermore, this state should be invariant under an arbitrary permutation of the B systems. So you swap them around and it's invariant. Okay. And how is this connected to separability? Well, every separable state is K extendable for all K. Why is that? If a state is separable, you can write it as a convex combination of product states. This is a theta. Sorry for the messy notation. So it's a convex combination of product states, every separable state. And so what do you take as the K extension? You just take this state and you can repeat it K times. That's a legitimate state. It's permutation invariant under swaps of the B systems. And when you trace out B2 through BK, you get back this state. Okay, so that's a link between K extendability and separability. And then a stronger link is that it's possible to prove that every entangled state is unextendable for some K, and then for every K prime larger than that K, it's also unextendable. Okay, and so you have this hierarchy where you have the two extendable states, that contains the three extendable states, contains the four extendable, all the way to K infinity. When K is infinity, that actually coincides with the separable states. I didn't argue for that, but it's true. And then if you want, precise connections between K extendability and separability, this kind of stuff is known, and it's given by what's called Definetti theorems. Okay. So what I'm going to tell you about is a new work in preparation, and this part is strongly linked to the prior work with Hayden, but we figured things out a bit more carefully. So Marguerite Laborde is a student at LSU, and we'll be putting this in the archive any day now, whenever it's ready. Okay. So one thing we show in this work, which does follow from some earlier results, is that a state rho AB is K extendable, according to the definition I just presented, if and only if there exists a purification where not only do you have these systems that extend B, but it's basically like we double everything. So we double the A system, we put a hat, and we double all the B systems with a hat as well. So a state rho AB is K extendable if and only if there exists a purification such that this is satisfied. This W pi is a unitary representation of a permutation of K systems. And the psi the purification is invariant under a tensor product of these permutation unitaries, okay? And that's for all possible unitaries. So then we can use this fact to test for K extendability in a QIP2 algorithm, okay? Now I've depicted the algorithm here, and it's kind of a natural thing, right? So like one thing we know in quantum information is that every purification of a state is related to another purification by a unitary, right? So what's going on is we have the circuit to make the state rho AB. That generates one purification of rho AB if we hold on to the reference. Then if the state is separable by everything I discussed, it should be possible to make another purification that satisfies this condition, okay? And by this principle that every purification is related by a unitary, there exists some unitary that relates to purifications. That's going to be hard to do in general, but that's what we asked the prover to do in the model, in the QIP2 quantum computational model. So we send the reference, we generate the state. Instead of discarding the reference, we send it to the prover. We then ask the prover to do the unitary that relates this purification to this one, in the case that the state's separable or K extendable, okay? And so all these systems come out, and then we want to test whether this condition holds. How do we do it? We use a variant of the quantum phase estimation algorithm, right? So this is a quantum computational test for permutation symmetry. So what's going on here is that we do a quantum Fourier transform to prepare the state in a uniform superposition of all possible permutations. And then controlled in the value of the permutation, we do this W pi. And we do the same here on these ones, okay? Then we do the inverse quantum Fourier transform, and we accept if and only if the all zeros outcome occurs. So what is the intuition? Well, if the state's K extendable, then by this theorem, this permutation exists. And so when we do this test, the state is permutation variant. And so there's no signal that will be sent back. There's no phase kickback that will be sent back, and will indeed measure the all zeros outcome, okay? But if the state is entangled, then this condition cannot hold for some K, right? That's what we stated earlier, some facts about entanglement. So, this test will fail with some probability if the state's entangled. Yes, so I mentioned this intuition, right? If the state rho AB is K extendable, then there exists a purification satisfying this star, this equation. And then the prover can act on the purifying system to take one purification to another. What we prove in our paper is something very interesting, and it's related to statements in the earlier paper with Patrick Hayden and Kevin Milner. We can prove that the acceptance probability of this QIP2 algorithm is the maximum K extendable fidelity. That's not obvious, and I don't have time to explain it. But if you're interested in that, I could send the draft, or you'll just see it in a week. So it's interesting because it gives this interactive proof system gives a precise operational meaning to the maximum K extendable fidelity, which is this quantity of interest, right? So it measures the closeness of rho AB to the set of K extendable states. Okay, so one idea that we're doing in the unpublished work is something I mentioned earlier that these other papers were already doing. Let's take the prover in this QIP2 algorithm. Let's replace the prover with a variational circuit and see how well we can estimate this maximum K extendable fidelity. And then that allows us to understand how entangled this state rho AB is. So it's like we have a way of measuring entanglement using a quantum computer. Okay. One thing that I'll just state is that for small circuit sizes, well, in general, if you have a description of rho AB as a matrix, the whole talk we've been talking about rho AB being generated by a circuit. If we have a description as a matrix, then this quantity can be calculated by means of a semi-definite program on a classical computer. Okay, so what we can do is for small circuit sizes, we can compare, we can benchmark the performance of the variational quantum algorithm with the true value from the semi-definite program. All right, I am hitting time quite rapidly. I want to tell you about one more thing, and then I'm going to stop. And the next thing is going to be very similar to the previous thing, so I'm going to talk about it fast. This is a method for testing symmetry on quantum computers. And this is the other thing. This is actually the main theme of the paper with Marguerite. So the problem is this: given a state rho S and the unitary representation of a group, decide whether the state rho S is symmetric with respect to these unitaries. So that means that this equality holds for all elements of the group. So symmetry comes up all the time in physics. And so this is something of interest in general, and if you study resource theories and quantum information theory, this is directly related to what's called resource theory of asymmetry. The idea there is that states that don't satisfy the symmetry are resourceful for some task, maybe in timekeeping, states that are, uniform superpositions of energy eigenstates of a Hamiltonian. They're asymmetric with respect to the Hamiltonian. They don't commute with the Hamiltonian, so they're good for timekeeping. That's an example. Okay. One theorem that we prove is that the state rho S is symmetric, very similar to the previous theorem, if and only if there's a purification psi RS of rho S that satisfies this equation. Here we have the unitary, these unitaries representations of the group, and then this bar means complex conjugate. So this condition will hold. Once we have this is something we can test on a quantum computer, right? So the algorithm is very similar. The QIP2 algorithm is this: prepare the state, send the reference to the prover. If the state's symmetric, the prover should be able to take one purification to another, right? The original purification is this one that generates the state rho S after tracing over R. The other purification is one that satisfies this, if the state's symmetric. So you ask the prover to do that, the prover sends back the reference. Again, you do the quantum phase estimation algorithm. You accept if and only if all zeros outcome occurs. So the reasoning behind this is similar to before with K extendability. And the acceptance probability is equal to the maximum symmetric fidelity. So it's the fidelity of rho to the state that's symmetric and like closest in fidelity. So that's very interesting. Not only does it give us a way to decide whether a state is symmetric, but the quantum algorithm also allows us to quantify how symmetric it is. Okay, same idea as before, replace the prover with a variational circuit. I don't have time. This is a paper that we wrote in collaboration with John Watrous, where we use the same ideas that I'm discussing in all the previous examples to compute a quantity of physical interest called fidelity of recovery. Okay, let me wrap up. The main thing I wanted to communicate is the tight link between quantum information theoretic reasoning and this quantum interactive proof model of computation. Okay, so it's an interesting link. I find it very fascinating, and it's nice if you know quantum information theory, then you can contribute to another topic. Okay, and then what are we seeing more recently? Let's replace the role of the prover with a variational circuit and see how good performance would be. For small circuit sizes, we can benchmark the performance of the quantum computer using semi-definite programs. In the future, it would be great to have more rigorous results about variational circuits, like to have a better sense of for what kinds of states can we accurately estimate the fidelity. You know, Patrick Coles and his group members at Los Alamos, they gave algorithms for estimating fidelity of states with low rank. You know, and recently there was a group who was in Australia who used the quantum singular value transform algorithm to estimate fidelity. So that would be interesting as to, you know, for what kinds of circuits that generate states can these variational techniques actually work well. All right, with that, I'll stop. Thank you.
Okay, so we have time for maybe about one question. If anybody wants to either raise their hand and unmute, or you can just unmute and ask it. Yes, Steph Folds.
Yeah, hiya. So I wanted to ask about the entanglement test that you talked about for mixed states.
Yeah.
Like with the swap test, it can't be a test for separability. Is that also true here? Like you'll never have confidence that it's a separate state.
That's true. Yeah.
Okay.
So that's exactly right. What it computes is this maximum K extendable fidelity. As K, if you make K larger and larger, then, you know, the set of K extendable states converges to the set of separable states. And then there are precise relations between, like, how close is the set of K extendable states to the set of separable states. And, you know, so there are estimates in trace norm, which depend badly on the dimension. But then for this other kind of norm called one-way LOCC norm, the dependence is better. It's just logarithmic in the dimension. So if you look at that paper that I wrote with Patrick Hayden and Kevin Milner, we phrased the complexity theoretic problem in a particular way. In terms of the trace norm and the one-way LCC norm. It's a little funny, but it's a way that we phrased it such that we can prove that the problem is in QIP2. And it's still an open question to do the quantum computational version of the separability problem with exclusive of the trace norm. And that's something I had worked on with Gus Kotowski quite some years ago, but we didn't publish anything. It's still open.
Thank you.
Any other questions?
I think I saw Hao Jian with a hand raised. I don't know.
Do you have a question, Hajong?
No, I didn't raise my hand. Sorry, I didn't.
Oh,
Okay.
okay.
Maybe it's a clap.
Yeah. Nice
Okay.
talk. Thank you.
Okay, so maybe I'll wait 5 seconds in case anybody else wants to unmute. Okay, so let's thank Professor Wilde one more time.
Thank you. Oh, if anyone is interested in discussions for a few minutes, I could do that. I don't know if it could be on this Zoom link or another one. If this Zoom call has to end, then you can email me and I can send a Zoom link.